So this lecture we're going to talk about topological sorting, and the first part of the lecture is about how to store graph data. So before we work with implicit graphs, for example grid, but now we'll be dealing with graphs that are explicitly specified. So a graph is a set of nodes connected by edges, and there are different kinds of graphs. These edges can be weighted, meaning that they have different values. So for example, here, this example on the left is a weighted graph. And it can also be unweighted, which essentially is saying all the edges are the same, so they all have weight 1 if you want to consider that. And in some graphs, weights can be negative. And edges can also be either undirected or directed. So if it's undirected, then that means you can go both directions on this edge. But if it's directed, then you can only go from one way to the other. So direction matters. So in simple graphs, there's no edge from a node to itself, and between two nodes, so between from a source to a destination, there's at most one edge. So for example, in this directed graph, we have one edge from A to B. We don't have sort of two edges from A to B. So then if we don't have that, and we don't have edges connecting a node to itself, then that is a simple graph. And I guess most of the graph we are dealing with, the edges may have a weight, and the nodes, oftentimes it doesn't have any other information. So for our purpose, node is really just an abstract thing so that they are connected by edges. But there are cases where nodes may also hold additional data, especially if we are talking about graphs in real life. So to store a graph, we need to store both information about the set of the nodes and the set of edges. And when the nodes do not have any interesting information, then we oftentimes don't explicitly store a set of nodes. So they're simply numbered, for example, from 0 to n-1 or from 1 to n, depending on one's preference. But edges have to be stored in some way. And the storage of the edges need to support operations that we want to perform on those edges. And these, depending on the algorithms, will differ. So for example, oftentimes we will need to retrieve all edges that are connected to a node. So this will be the case when we do topological sorting. Given a node, we want to know all the edges that from this node we can go out to. And sometimes we need to test if two nodes are whether they are directly connected. And sometimes we just want to loop through all the edges. So depending on which operation we need to perform and the desired efficiency, we may choose different ways for representing the edges. Probably the most common way for representing edges is to use adjacency list, which we will talk about on the next slide in more detail. Essentially, it stores for every node a list of edges that are adjacent to this node. And sometimes we may use adjacency matrices, where there's a matrix where every cell describes the information between any two nodes in the graph. And sometimes we are given an edge list, which essentially just store all the edges in a single array. So for some algorithm, this is perfectly fine. So some algorithm just process one edge at a time. They don't really care about grouping all the edges that are connected to one node together, which is what adjacency list does. And also we've worked quite a bit with implicit graph before. For example, on a grid, if we can move in 4 directions, that is essentially an implicit graph. So implicit graph sort of directly support both adjacency list operation, which is given a node finding out all the edges connected to it, and also directly support adjacency matrix operation, basically checking whether two nodes are directly connected. So when we are working with implicit graph, it's sort of kind of nice. We don't need any additional, oftentimes we don't need any additional representation of the edge information. Okay, so adjacency list enables the operation of enumerating all edges that are connected to a single node. So for every node, we want to store a list of edges starting at that node. And if it's weighted graph, we will want to store both the destination node and the weight of the edge. So typically, we will use we can use typically we will use array list of array list in Java. Because oftentimes we don't know exactly how many number of edges there are for a node, so the length cannot be determined ahead of time. So we use array list instead of array, and we cannot define an array of array list, so we have to use array list of array list. And one thing to note is that for directed graph, every edge will appear just once. But for undirected graph, each edge will appear twice. Each edge, we will be able to see each edge both from, so given an edge connecting node U and V, we should be able to traverse that edge, find that edge. When we are looking at U, we should also be able to find that edge when we are looking at V. So depending on what we need to do, sometime for directed graph, we want to store two different kind of adjacency list, one for the outgoing edges, the other for incoming edges. And oftentimes this adjacency list is necessary. We have to use it instead of, so given a graph with n nodes, there are at most n choose 2, which is n times n minus 1 over 2 edges for a simple undirected graph. So if the number of edges is significantly less than that, we don't want to pay the quadratic cost of both memory and also in terms of processing. So we have to use the adjacency list representation. And this adjacency list can represent non-simple graph if that is if the graph is non-simple, meaning that for example, there may be more than one edge connecting two nodes. Okay. Now for adjacency matrix, it stores edges as values in a n by n matrix, assuming there are n nodes. And the matrix cell, matrix ij, corresponding with the edge from node I to node j. And for weighted graph, we will store the weight as the value in the matrix. For unweighted graph, this matrix typically is binary, just a 1 or 0. So so we are going to revisit this adjacency matrix representation when we use it. For this topic, we will be using adjacency list.